Okay, in this video I am going to derive the integrating factor method. This is not something you need to know for the further maths course, however, I do think it's useful to know the how and why this method is what it is. So this method applies to a first order linear differential equation, and it can be applied in theory to any, although there are some integrals that just cannot be done. But on this course, all the integrals that you'll come across in this method are ones that can be executed. So the general first order linear differential equation can be written like this. So we have one first order derivative, we have the 0th order derivative, or the function itself, times some function of x, and that's going to equal some other function of x. It is important that we have a coefficient of 1 for the first derivative. If it is anything other than the number 1, then you need to divide by that function of x, or that constant, to make it a 1 so that it looks like this. Okay, it's got to look like this. Okay, so what this method does is it takes advantage of the product rule from differentiation. So what we try and do is we try and essentially factorize this left-hand side. So instead of having y appearing in two places, we have a y appearing once, and we arrive at that using reversing the product rule. So what I'm going to do is I'm going to take this whole equation and I'm going to times it by something that I'm going to call I of x. Now, I of x is what we call the integrating factor. It is a very particular function, and for now it's just going to be a function, and we'll derive what it is in terms of p and q shortly. So in terms, take this whole equation to times it by I. So I get I times dy by dx plus I of x times p of x. I of x is just a function of x, okay? Don't be scared of it. It's just a function of x. We just don't know what it is yet. Okay, so just times the whole equation by I of x. And I of x is chosen very specifically so that this left-hand side can be written as the derivative of the product of I of x and y. Okay, I of x is chosen specifically so that this factorization can take place. And that's going to equal this function over here, which is at the moment written as two functions of x times together, but in general just be a function of x over here. And then what we can do is we can now make essentially y the subject. So we'd integrate both sides, and then we divide by I. So if I integrate both sides, I'll get I of x y is equal to the integral of I of x q of x, assuming that integral can be done. Okay, and then finally divide the whole thing by I. So the integral of I of x q of x dx divided by I of x. Just be careful, you can't cancel the i's of x here, because this I is within that integral and this I is outside of the integral, so you can't cancel those i's. Okay, and we've made y then as a function of x. So that's the idea of this, and the clever part is the choice of I such that this factorization can take place. Okay, so that's what we're going to look at now. So using the product rule on this, what we're going to get is we're going to get this times the differential of this, which is I of x times dy by dx, okay, which is that first term anyway. So that times the differential of that gives us that. So that's there. And then by the product rule, we also need that times the differential of that. So we're going to get plus I primed of x, the differential of whatever I is, times y. And we need these two to be the same so that this can be written as this. And that is the key bit of information here. This is obviously true for all I, and it's this part. You need these to be the same, and that'll allow us to define I. So if I take those two bits there circled in green, okay, the coefficient of y, if you like, I primed of x needs to equal I of x times p of x. Okay, so I primed of x needs to equal I of x times p of x. Okay, the coefficient of y, I primed, needs to equal the coefficient of y, which is ip. Okay, so this is another differential equation, but we can separate the variables on this one. So let's just rewrite it in a slightly different format. So I primed is actually just di by dx. That's what I primed means. That's I, and that's p. And we can separate the variables here. So if I divide by I and times by dx, I'll end up with 1 over I di equals p dx. And then if I pop an integral symbol on both sides, I've separated the variables. P is a function of x, so that's okay. And 1 over I di integrated is the natural log of technically mod of I, but I'm going to exponentiate in a minute anyway, so that'll get rid of the mod. And that's the integral of p of x dx. Okay, this is obviously going to vary depending on what p is. It's going to change from question to question. And then finally, exponentiate both sides, and I end up with I, my function of x, is equal to e to the integral of p of x dx. Okay. A couple of important points to note at this stage. This is how we define I. This is you can jump straight from this question to the definition of I. Then you can state that this can be written as this when you're answering it in a question. Second point to notice is this whole process requires two integrals. We've got an integral here in the actual method, and then we've got an integral here in our definition of I. It is a first order differential equation, so we only need one arbitrary constant, and the arbitrary constant comes from this integral here. Okay, when we integrate this, that's going to give us an arbitrary constant for our differential equation. The constant, or the arbitrary constant that we could, in theory, get from here is redundant. We don't need it, so we just ignore it. And the reason we don't need it is because if we have a plus c in this exponent, all that's going to do is multiply this exponential by a constant, which is the same as multiplying this whole differential equation by a constant. So it doesn't do anything. It is unnecessary for the method. So in the definition of I, here, when we integrate p, we do not include the arbitrary constant here. Okay, but we must include the arbitrary constant in this integral here. Okay, so that's the process. In the next video, at least, we're going to look at some examples of this in action. It's a very clever little method, and it's something you need for Core Pure for further mathematics A level. All right, thank you very much for watching.